one of the things that you are going to expect on most any exams, in any general chemistry class or any standardized exams to see what somebody knows in chemistry, is can you write the electron configuration, the ground state electron configuration, for an atom or ion. And so there's a couple of things that I always want to make sure I'm ready for when I'm going to write electron configurations. One is I need the proper filling order for orbitals. So you start with the 1s, the first energy level. Then the second energy level has 2s and 2p sublevels. The third energy level has 3s, 3p, and 3d sublevels. But as we've seen before, in neutral elements you have to fill the 4s sublevel before you can start filling the 3d sublevel if you're looking for the ground state for neutral atoms. And you can see this filling order by following along the atomic numbers in the periodic table. If you understand the map, you can try to just remember this ordering, or you can go ahead and construct a little diagram with arrows through the orbitals, which I've always disliked. But there's several strategies. Any way you look at it, you need to have the orbitals in the right energy ordering in order to write the electron configurations. So you have 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, and I believe that's enough room for electrons to accommodate calcium, calcium 2 plus, or selenium. So if you have the right orbital ordering, check, you're ready to begin. The next thing that's really important is the number of electrons that you need to accommodate. So if you look at the periodic table, you have calcium. Calcium has 20 electrons. You can look and find it in the S block. Calcium is element 20. If it's a neutral atom with no charge, it's going to have 20 electrons. So if you have 20 electrons, you can go ahead and start filling. Now, one of the other things I do, if it's a neutral atom, I look at the periodic table and see, is it in the S block? If so, my outer electron should be in s orbitals. Is it in the p block? If so, my outer electron should be in p orbitals. Calcium is in the second column of the 4s row, so I'm expecting it to end with 4s2 as the neutral element. So let's go ahead and fill them and see how that works out. We have 1s2, 2s2, 2p6, it's 10 electrons, halfway there, 3s2, 3p6, 4s2, that's 2, 4, 10, 12, 18, 20 electrons. And we did end, as expected, based on the location of calcium on the periodic table, end with the 4s2 configuration. So again, where did I get that from? Hydrogen is the 1s, lithium is the 2s, sodium is the 3s, potassium is the 4s, and I apologize, it looks like the lighting is terrible for this. 1s, 2s, 3s, 4s, 2. 4s1, 4s2. Calcium I expect to end with 4s2 based on its location in the periodic table. If I fill in 20 electrons from the lowest energy on up, that's where it ends. So this looks like the right electron configuration for calcium. For calcium 2 plus, I have to ask myself, how did it become calcium 2 plus? Why, you get to be positively charged if you lose the negatively charged electrons. So when I see the 2 plus, I know that this species lost 2 electrons compared to what it originally had. So if a neutral calcium has 20 electrons, calcium 2 plus is going to have 18 electrons, and the electrons it generally loses would be the outermost electrons, are furthest away from the nucleus and easiest to remove. So if nothing funny happens, you just take the 2 outer electrons from calcium to make calcium 2 plus, 18 electrons, 1s2, 2s2, 2p6, 3s2, 3p6. So there's how to account for 18 electrons. Calcium, we accounted for 20 electrons. Calcium 2 plus, we account for 18 electrons in the lowest possible orbitals. Alright, and then selenium. We look at selenium in the periodic table and we see that has 34 electrons. Right, 34 electrons. And if I look at the location of selenium in the periodic table, over here in the not obscured part of the video, carbon would be the 2p, silicon would be the 3p, germanium would be the 4p, tin and its row would be the 5p. So I see selenium in here in the row with germanium, 2, 3, 4p, and then it's the 1, 2, 3, 4th column of the 4p group. So I'm expecting selenium to end with 4p4. Now I didn't do this exercise with the ion because this map of the periodic table and how they correspond to electron configurations only applies to neutral elements. So if I look at a neutral selenium, 34 electrons, it sits in the 4th column of the 4p row, so I expect its electron configuration to end with 4p4. So I go ahead and fill out 1s2, 2s2, 2p6, 3s2, 3p6, right? 4s2, 3d10, 4p4. So I start at the lowest sublevel, and I just fill in increasing energies until I get to my predicted stopping point, 4p4. Now I'm going to see if I accounted for all the electrons. 2, 4, 10, 12, 18, 20, 30, 34 electrons. Check. It looks like this is a good electron configuration for selenium. And one of the things that oftentimes people want to do is save some time and energy. So we've invented sort of a shortcut for writing the electron configurations. For the inner electrons, they're not very reactive, so we don't really need to know where they are. The outer electrons are the reactive ones. Those are the ones other elements bump into, take, etc. So we're not necessarily need to see all the detail of where the inner electrons are. So for noble gas in brackets, like neon in brackets, says this is the electron configuration for neon, so it means the same as 1s2, 2s2, 2p6. So if I wanted to just write 1s2, 2s2, 2p6 quickly, I could write neon in brackets. If I go to the next noble gas, argon, and put that in brackets, that's got an element with 18 electrons. So this accounts for the lowest 18 electrons. 1s2, 2s2, 2p6, 3s2, 3p6. If I put an argon in brackets, it means the same thing as 1s2, 2s2, 2p6, 3s2, 3p6. And these electrons are going to be fairly unreactive, nice filled shell. So if I see calcium 2 plus here, that's the exact same configuration as argon. So the electron configuration of calcium 2 plus I could summarize with just argon in brackets, because that's the electron configuration of argon. It's also the electron configuration of calcium 2 plus. Now for the calcium, we had the electron configuration of argon plus the 4s2, so I could rewrite this as argon in brackets, 4s2, and that's the abbreviated way to write the electron configuration of calcium that shows the 18 unreactive electrons and the 2 that are ready to react or get involved with other atoms. So here's 3 examples of electron configurations: 2 atoms and an ion, calcium, selenium, and the calcium 2 plus ion. If you want me to do any other examples, you can send me an email and I'll try to work them out. Maybe I'll make another video with a couple more examples.